This video shows 21-year-old Shayna Richardson spinning out of control in her first solo skydiving jump. It happened October 9th in the skies over Arkansas. After jumping out of the plane, Richardson's main parachute failed. When she tried to open her backup parachute, it would not open all the way. As her frightening downward spiral continued at about 50 miles per hour, Richardson says she was sure she would crash and die. She was half correct. Richardson did hit the ground, smashing face first in a parking lot. But amazingly, she survived. Richardson broke her pelvis and her leg and lost 6 teeth. After 4 surgeries, she now has 15 steel plates embedded in her body. There was also an unexpected surprise. Shayna Richardson is pregnant.
Wow, what a day. All right, so let's go back.
Richardson hit the ground, smashing face first in a parking lot. But amazingly, she first in a parking lot. Half correct. Crash and die. She was half correct. Richardson did hit the ground, smashing face first in a parking lot. But amazingly, she survived the way. As her frightening downward spiral continued at about 50 miles per hour, Richardson says she was sure she would crash and die. She was half correct. Richardson did hit the ground, smashing face first in a parking lot.
Smashing face first against concrete at 50 miles per hour. How did she survive the impact at 50 miles per hour? What made that survivable? All right, guys, what do you think?
Parachute when you took some of the speed off?
Okay, I'm sorry, say it again. No, with the parachute, she's going down at 50 miles per hour. Without the parachute, whatever, around 120 miles per hour. So, surviving impact at 50 miles per hour, parachute has nothing to do with it. So, she's already going down at 50 miles per hour with face first. She hits the ground with face first. She hits concrete with her face first. So, how did she survive the initial impact? What made it survivable? So, we're still talking about acceleration, right? So, what increases impact? What increases impact on you guys? Crumple zone now, right? So do you think her face acted like a crumple zone? Is that what it is?
O'Neill says, once again, this round of testing shows you don't have to buy an expensive car to buy safety. But the heavier the vehicle, the better, simply because there is more metal between you and the crash. What's the difference in being in an accident at 40 miles an hour in a vehicle that is rated a best pick versus one that only gets a 4?
Well, if you're in a serious frontal crash in one of our good performing vehicles, one that's the best pick, there's a very good chance that you can walk away from that crash without any serious injuries. If, on the other hand, you're in a vehicle that we've rated as a poor performer, there's a very good chance that you're going to have multiple fractures of the leg, maybe even very serious injuries all the way, including potentially fatal injuries to the head.
So, at 40 miles per hour, 40 to 50 miles per hour, car crashes, you experience about 20 to 25 Gs. So how much of a crumple zone do you need in order to survive this at 20 to 25 Gs? Predictable motion. The first thing you need to do is you need to take something chaotic, like a car collision or impact, and then make predictable motion out of it. So what's considered predictable motion?
This is the most complex and sophisticated machine ever made. In 6 minutes, it will be traveling at 17,500 miles an hour. In 8 minutes, the humans inside will no longer feel the pull of the Earth's gravity.
You're on mute, Professor.
So thank you. Yourself 5 points. So space shuttle takes about 8 minutes, 6 to 8 minutes to entire space shuttle run. Within that 8 minutes, it travels 180 miles while reaching the final speed of 17,500 miles per hour. Now, within that 8 minutes, no one is in charge of piloting the space shuttle. So within that duration, every single aspect of motion needs to be made predictable. So how does NASA make motion predictable? So you got 8 minutes to get to the orbit, and you will travel 180 miles from the surface of the Earth while reaching the orbital speed of 17,500 miles per hour. So these are the limits within which the space shuttle needs to function. And within that 8 minutes, no one is in charge of piloting the space shuttle. So which means that for that duration, every single aspect of motion needs to be made predictable. So the question is, how does NASA make motion predictable?
1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it is...
Though it started out as a grand achievement for NASA, 73 seconds later turned into a national tragedy.
Just because you got rockets doesn't mean that you're going anywhere. They were able to get 73 seconds of predictable motion. And then the chaos ensued. I mean, obviously you need rockets in order to get anywhere. But with rockets, you're dealing with explosives in general.
Rockets aren't new. Neither is the idea of riding them to the heavens. One night in the 16th century, a Chinese nobleman, Wan Hu, prepared himself for liftoff. But then there was, as modern spacemen say, a glitch. And though Wan Hu didn't make it to the stars, he couldn't be found on the face of the Earth either.
So the Chinese got the right idea. Yes, you do need rockets. But with rockets, inherently, you're dealing with explosives. So how do you take something chaotic, explosive, and then make predictable motion out of it? So the question is, what is considered a predictable motion?
There is no
Predictable motion is any motion that allows forecasting.
danger,
For
however,
example, a satellite coming down back to Earth.
as the satellite's now expected to...
You'll know exactly where it's going to land, as well as how fast it's going to land. That information is going to be 100% predictable.
smash into Quasi, an uninhabited part of the Australian outback. Scientists say the following.
So this guy knows that he's on the landing spot. Motion is so predictable that he's able to order enough pillows to cushion the impact. First, that not only is he ready for impact.
Do you, Yahoo?
So it's his dog. So that's predictable motion for him. So how do you make motion predictable? How does NASA make motion predictable? It's an extension of the previous one. Well, let's do it quickly. All right, so displacement in time is your velocity. So measured distance over measured time. Velocity is a combination of speed and direction. How fast your velocity changes in time. Change in measured velocity in time is your acceleration. That's how fast you speed up, slow down, or change direction. So speeding up is acceleration. Change in direction is acceleration. Speeding up, slowing down, or changing direction is acceleration. Notice that unimpacted acceleration is about to change. So changing acceleration in time, what do we call that? So changing acceleration in time, what is that called? Okay, so that's as far as we got so far. All right, so we're gonna move on to some little bit mathematical at this point. So changing acceleration in time. All right, so here's a fast review of what we already know. Measured distance over measured time is going to give you your velocity. All right, so measured distance over measured time. This thing is getting displaced within this time period because of its velocity. So this thing is your velocity. Measured distance over measured time is your average velocity. If your instantaneous velocity is changing in time, so it goes from an initial value to some final value. We say we call this acceleration. This is your average acceleration. So velocity is changing in time, which means that it's accelerating. So now what's about to happen is your acceleration is going to change on impact. So you will go one acceleration to a different acceleration within this time period. So change in acceleration. What do we call this? All right, so we use the letter J. J means jerk. The motion is called jerking motion. So changing acceleration in time is called jerk. The motion itself is called jerking motion. It's a technical term. All right, so measured distance over measured time is going to give your average velocity. Change in measured velocity in time is going to give your average acceleration. Change in measured acceleration in time is going to give you your average jerk. So, average velocity, average acceleration, and average jerk. So, change in acceleration in time means the measured acceleration is changing in time within this time period. Change in instantaneous acceleration in time. All right, the problem with jerking motion is it's chaotic motion. It's chaos. Example of jerking motion that we've seen so far is car collision. Car collision is a jerking motion because within 1/10 of a second, as the engine compartment is crumpling, acceleration changes 1,000 times, 1,000,000 times, because the different portions of the car is going to crumple at different rates. All right, so let's express the acceleration in terms of g's. Here's what a car collision looks like within 1/10 of a second. Acceleration is just you jump around. It does this. It's going to go up and down, up and down, up and down, and then it just stops. All right, so the entire thing that you're looking at lasts only 1/10 of a second. And then if you're looking at the acceleration, notice that the acceleration values are changing. You peak here, you peak here, you peak here, you peak here. It goes up and down, up and down. All right, so it ends up peaking at different points. So if that's the case, which acceleration value are we going to use for during jerk while the engine compartment is crumpling? Well, you can look at the maximum value. It's probably, I'm just going to make something up. This could be 120 Gs. Or I'm going to make it 150 Gs because 140 is as far as you can go. So given the fact that the maximum acceleration during the crash is 150 Gs, that's survivable. If you're looking at the peak acceleration, you will say, no, of course it's not survivable. That's one of the problems that the Mythbusters used to have. They used to drive me nuts. I love the show. And they would always look at the peak acceleration, and then they would come up with these erroneous conclusions. It's not the peak acceleration. The peak acceleration is going to be 150 Gs. That doesn't mean anything. You have to take a look at what happens to this value. You need to look at the average value. Notice that the average value is going to be around 20 Gs. So if there is jerking motion, this is going to be 20 Gs. This is going to be 120, 50 Gs. If there is jerking motion, what we do is we use the average acceleration. So jerk, which is that, simply implies that the acceleration is changing in time. Because the acceleration is changing in time, what we do is we use the average acceleration. That's what we do. So when there's jerking motion, we don't care how much the acceleration is changing. The only thing we care is if there's change in acceleration. We use the average acceleration formula. We use the average acceleration because average acceleration tells us whether it's deadly or survivable. That's what it is. All right, so jerking motion itself is chaotic motion. And the prime example of jerking motion that we've discussed so far is the car collision. And when there's jerking motion, we use average acceleration. We're only interested in the average value because average value is what determines whether it's survivable or deadly. All right, so changing acceleration in time is called jerk, and the motion is called jerking motion. All right, jerking motion is just a formula indicating that acceleration is changing in time. You do not use jerk for numerical reasons. So generating numbers using that formula does not really give you anything significant. So if there's jerking motion, we use average acceleration to figure out if it's safe or if it's deadly. The prime example of jerk or jerking motion